It's really great to be here. My name is Sean, and I'm going to be discussing state proofs and their lesser known applications. So, state proofs are actually this very critical piece of blockchain technology that power quite a lot of things, including trustless bridges, light clients, modular chains that allow you to have this L2, L3 architecture. But I guess not a lot of people know how they work and why they work. And in this talk, I'll be trying to demystify state proofs and their mechanism of operation. So first off, I think it's very important to understand blockchains as state machines, right? So every block holds some state. We will just think of this state as some object data format, and every time a transaction is applied in a new block, you end up with a new state. And a blockchain really is this state transition function that takes the previous state, applies some transactions, these transactions encode how the state should be modified, and you end up with a new state, right? And so, there's some issues with this. Because if you need to execute a block, then you essentially have to execute all the transactions. And this is something that Seun just also recently discussed in his talk about ZK proofs of blockchains. And so, we'll actually look at what the format of this state is, and what the state is. Essentially, it's a Merkle tree. Merkle trees essentially allow us to cryptographically commit to some information. In this case, you could just think of this as a flat list of data, and you just recursively hash pairs of this data up until you get to a single root element. Some beautiful properties about this is that you get these log n proofs. So if you needed to prove that any single item in the list existed in the root, in the commitment, then you could just get a log n size proof of this. You could partially reveal this list without having to reveal the entire list. And it's tamper resistant, depending on the security of your hash function. And because of the way hash functions work, you have up to 128 bits of security. So we'll actually look at what the Ethereum and most popular blockchains use, which is the Merkle-Patricia tree. And in this kind of Merkle tree, the keys are encoded in the path to the data. So instead of having a flat list, you actually have this map structure, and then you have keys that point to a leaf to the actual data. And then each key, or nibbles as they're called, is encoded in the path to the data. And so in the Merkle-Patricia tree, you actually have 16 branches. That's why it's called a hexary tree. And you have different kinds of nodes. You have essentially the root node, you have the branch nodes, you have the leaf nodes, you have the extension nodes, right? And if you go on Etherscan today and you pull up any Ethereum block, you're always going to find this thing called the state root. It's basically the commitment to all of Ethereum's state, so all the accounts, all the smart contract storage. There's so many of them, and every node essentially has to create this commitment for every block, right? And so this is essentially all the different kinds of proofs you can obtain today from, I would say, most popular EVM chains. Not a lot of EVM chains have state proofs, I would say that. But the most popular ones: Polygon, BNB chain, Ethereum L1, all the L2s. In fact, the L2s have to have state proofs, otherwise they would not be L2s, right? And I'll get into that later. But essentially, you can get proofs for each account in the state, right? So account has this property of the nonce, the code hash, the balance, I think the storage root if it's a contract. And you could get storage proofs of independent or individual slot hashes in a smart contract storage layout. Or you could just get the full state proof, right? You want to prove that some data exists in some smart contract slot hash, and you need to prove that all the way up to the state roots. So, let's look at what are the applications for this. Like, why do we have state proofs? So primarily, it's for interoperability. Because blockchains are essentially committing to the state of all the smart contract storage data, then we can actually tell other blockchains what's happening on chain on a different blockchain, right? Because we can acquire these proofs, and if the receiving blockchain is able to verify these proofs, if the maybe verification algorithm is not too complex, then this blockchain can actually learn trustlessly what is happening on chain. And there's different applications for interoperability, right? You can have token bridging, you can have lending, you can have all kinds of applications that require interoperability. And there's already a few examples of protocols today, interoperability protocols that require state proofs. One of them is, of course, Hyperbridge. But then you also have things like IBC, which comes from the Cosmos ecosystem. And you also have L2 bridges. And L2 bridges primarily work by having a state commitment that is posted to Ethereum. And you can then prove things about that state routes to maybe exit, bridges, exit assets from the L2, or to actually communicate between the L1 and L2. Another application of state proofs is actually privacy. And now this goes over a lot of people's heads, but you see, the way that the future privacy protocols are going to work is that we're going to build privacy protocols on top of public blockchains. And the way that this is going to work is that you're going to be able to generate proofs of people making transactions on their personal chain. This notion of a personal roll-up, where you essentially create this transaction chain that's off-chain, but you use ZK proofs to update the state of your transaction chain, and then you're constantly posting state routes on-chain about what is the latest state of your personal chain. But if someone wanted to receive assets from your personal chain, then they would have to prove that in your personal rollup you've paid them, right? But then they would be essentially revealing who paid them, because they would have to point to your personal state route on chain. But because we're actually living in this Merkle tree, then we don't actually have to reveal which individual state route this payment is coming from. We can actually just point to the global state route and say, well, in the global state route, there's some account state route that hasn't paid me, and I can just prove that Merkle path all the way down to the payment transaction. So this is one of the ways in which I personally see privacy protocols essentially scaling through this personal roll-up architecture. And finally, I would say, state routes allow for scalability. Previously, consensus layers would bundle a single execution layer, which is where you now need to generate state proofs and state commitments about the execution layer. Now we're seeing the rise of consensus layers that are purely agnostic to execution. One of them, of course, being Ethereum, Polkadot, and of course more and more of these kinds of architectures are showing up. But how they work still goes back to using state routes, right? So essentially, you want to have a way to verify that what each execution shard is doing. And the way that you do this is you would typically have to re-execute the entire blocks of each shard. And to actually do this, you need to have the state proof of all the elements that are accessed in the state tree and a proof for them, so that you can compute what is the post-state route. And this is the way in which optimistic rollups work, even ZK rollups today. Each ZK rollup is essentially going to take what is the pre-state of the block that they're operating on, all of the Merkle proofs of all the items that are accessed by that block. They're going to execute the block, and they're going to essentially arrive at what is the post-state route. So this is more of a graphical representation of what ZK rollups are essentially doing. You have your pre-states, all the elements that are accessed in the pre-states, Merkle proofs for them. This will have to be verified, and then the ZK rollup essentially just computes what is the post-state route for that block. And then there's, of course, an upcoming improvement proposal for our Merkle Patricia tree. They're called Verkle trees, and previously we used to use hash-based cryptography. Verkle trees use polynomial schemes and polynomial commitment schemes, which can also be post-quantum if you're using things like FRI. You don't necessarily have to use KZG. And this could potentially make state proofs much more efficient and much more cheap to verify. So finally, we come to light clients. So, I think a lot of us, when we got into decentralization and we got into this whole meta, was that, okay, how exactly are people going to use blockchains, right? Is everyone going to have to run their own node? Because that's the only way in which we can actually trust the information that we're getting about the chain. And this is, of course, very expensive, right? I think Solana requires a whole data center. Ethereum maybe not so much, but still cumbersome to run. The way in which we can actually scale, blockchain data access to everyday people is through the use of these light clients, right? So rather than having to execute every block, you would instead have a light client that is able to follow the consensus of the chain. And if they need to basically query on-chain data, they would have to query this data with storage proofs, right? So remember, in the consensus metadata, we have the state roots, right? The header, we have the state roots, and then we can ask a full node, okay, what is my balance, or what is happening on this application? But we don't want full nodes to be able to lie to us, so we will ask the full node to present a Merkle proof, a state proof, to essentially authenticate what they're claiming, right? And so this is how most people will be able to use blockchains without having to essentially run data centers to keep up with the chains that they all know and love. So just want to basically summarize my talk. State proofs essentially allow for cryptographic verification of on-chain data. There's different schemes for this. You have your classic, binary Merkle trees. You have the Merkle-Patricia trees, and we have the upcoming Verkle trees. And they power trustless bridges and trustless interoperability protocols that don't rely on centralized multi-sigs or middlemen. They also enable privacy. For instance, Tornado Cash actually builds a Merkle tree on-chain, and that's a kind of Merkle proof that enables privacy. And they are also the foundation for future modular blockchain rollups. If you have any questions, I'm happy to answer now. If not, thank you for coming to my talk. Bye, everyone.